Good afternoon, everyone. This is Vishnu Shivan from Aegis Computers India Private Limited. I'm the host for today's webinar session. For your kind information, microphones and webcams are disabled for saving bandwidth. But don't worry, we shall have a Q&A section. You can ask your valuable questions at the end of session. It is my great pleasure to welcome you to this webinar session by Aegis Computers India Private Limited. Today, we have the honor of hearing from Mr. Natarajan Ramamurthy, the Managing Director of Aegis Computers India Private Limited, a distinguished leader in the field of product design, finite element analysis, design verification, validation, and development. Aegis India Chennai was started in 1993 to provide mechanical engineering consultancy services with main focus on new product design and development using niche technologies available in market. We are associated with Resolve Systems Solidworks Corporation USA since 1999 for providing CAD, CAE, PDM solutions to customers in varied industry segments. About our presenter, Mr. Natarajan Ramamurthy, Managing Director of Aegis India, has over 36 years of experience in product design, finite element analysis, design verification, validation, and development. His courses on FA are well known in the industry and academia. He has a master's degree in mechanical engineering from the University of Toledo, Ohio, USA, and started his career with Ford Motor Company. He has worked on development of product designs for braking systems, suspension systems, industrial instrument panel support structures, full vehicle systems using simulation tools as the mainstay in the design verification. An ASB certified GD&D technologist, he has been incorporating GD&D practices in product design and development in addition to consulting with industries in varied vertical segments. He is an active member of the Bureau of Indian Standards with MED section assisting in evolving standards for material handling equipments, in addition to the Drawing Standards Committee. Predictive engineering by evaluating failure modes and their effects corroborate with FEA. Effective FEA while addressing dimension variations has helped many industrial products achieve higher quality and reliability. Born out of decades of experience, his design for quality and reliability process is well adopted by engineering industries in India and rest of the world for the first time right achievements. Today's webinar, led by Mr. Natarajan Ramamurthy, will focus on the critical aspects of mechanical design, how to leverage design of experiments for higher quality and performance by design. Without further ado, please join me in welcoming Mr. Natarajan Ramamurthy. Sir.
Thank you, Vishnu. Good afternoon to all of you. Today's webinar topic is going to be on how to leverage design of experiments for higher quality and performance by design. A lot of times, design engineers are beset with the challenge, how much tolerance to give. What are really the parameters that are going to influence the performance required? What are the different types of performance challenges we'll face in our products and technologies that we come up with? What are the failure modes, whether they will affect the overall reliability of the system? Many questions are asked by design engineers for which many answers are still not available unless we physically develop the prototype and test it, and even then it is within a small window of limitations as far as the test is concerned. Design of experiments is something which is versatile, and its application in design engineering is so beautiful that one can use it as a powerful tool and say with confidence the reliability and the quality of the system can be met with a few tests here and there, which doesn't cost a whole lot as compared to physical prototyping and testing. Imagine if we were to take one parameter at a time and varying only one parameter at a time and trying to get the effect of that variable on that performance of the system. It would be very expensive to do it for the product having many parameters and many variables coming into play. The interrelationship between the variables also is under question. So now the design of experiments is something which has been there for quite some time. Let us go through the agenda briefly and then we will get started right away. First, a little bit about BGS India, and then what is DoE, the importance of DoE as applied to design optimization using DoE, the application of DoE in design with examples, and the benefits of this for the engineering community, and then we will field the question and answers towards the end. AGS India was started with the vision of engineering development through effective partnership with customers, through the mission statements, imparting leading edge technology, specifically through training and development, new product design and development through consulting services, and providing software solutions and technical support. AGS was started in the US in 1981 as AGS Incorporate USA, and the India operation started in 1993 when I returned from US after my tenure at Ford Motor Company as a design engineer. And then we started working in India quite a bit, and we started representing SRAC, which is a part of the Dassault Systems today, since 1997, and then subsequently went on to work with Dassault Systems Solidworks Corporation since 1999. We opened our first office outside of Chennai in Coimbatore, which has a significant presence, and we have grown quite a bit over there in AGS Coimbatore. We have a considerable presence, and then we have followed with Trichy operations. We have customers worldwide, and we started developing our own products indigenously in India in terms of the software technologies. The first product what we developed was the Live PLM, specifically for the manufacturing industry, followed by the Live QC tools, which we are launching imminently. We have 3 branches, Chennai, Coimbatore, and Trichy, with over 140 employees since 1993. And with over 22,000 customers and affiliation to the major industrial organizations in terms of CAE, IMTMA, IPI. We give guest lectures and training sessions at IMTMA. We give NIQR and many others. And innovation is the mainstay in every activity that we do, and we continuously improve the processes that we have established at AGS in tune with the customer requirements. The business model comprises of 3 segments. We started with the engineering services, which is our mainstay with regard to the impact that we have developed with regard to our customer products and technologies, followed by the software solutions, and then the technology training through our academics training division. We provide our flagship courses are in finite element analysis, geometric dimensioning and tolerancing, tolerance stack-up analysis, failure modes and effects analysis, DFM and DFA, and popular CAD FEA tools. Now, the tributes to the architects of DoE would be the first thing that we would start with before we go through this presentation. And one of the architects of the design of experiments is Professor C.R. Rao, who developed the theory of orthogonal arrays. He passed away last year at the age of 103. He used to give lectures at IIT Madras. He was the person who institutionalized the theory of orthogonal arrays to be subsequently used by Taguchi, Professor Jenichi Taguchi. He won the International Prize in Statistics in 2023 just before he passed away, which is equivalent to the Nobel Prize. And he is a distinguished mathematician and statistician. DoE would be poor without his contributions. We pay our tributes to this legend in the field of mathematics and statistics from India. And we should be proud of Professor C.R. Rao, who retired and went to the US and settled over there and continued his professional excellence by teaching over there at Penn State University. And he had a second career over there after he retired from Indian Statistical Institute, Kolkata. The other person is Professor Jenichi Taguchi, whose design of experiments is ubiquitous. There is an uncommon relationship between the 2 doyens. Professor Jenichi Taguchi was introduced to the orthogonal arrays theory by Professor C.R. Rao during a sabbatical at ISI Kolkata. And subsequently, he came up with the quadratic loss function and the implementation of the orthogonal arrays theory using the design of experiments. So he worked with the SQC unit of ISI with the inventor C.R. Rao. So what we know today as Taguchi methods, known worldwide, the genesis was in his deliberations with Professor C.R. Rao at ISI Kolkata. With this tribute, let us go on further. The design process where the DOE needs to be employed. We have been employing this in many products and technologies that we have developed for many customers in India and outside of India, whether it is two-wheeler industry, four-wheeler industry, electric vehicle industry, the valve industry, the actuator industry, the Ministry of Defense, any place where we have been working with in different varied vertical segments. This is exactly the process what we follow. If somebody asks us to do a root cause analysis for a failure, we follow the same process as well. And that's exactly where DOE finds its place. Nevertheless, this presentation is all about how to use DOE for design and development of new products and technologies. So quality and reliability are the two things which are mainstay in any product, and with these two being non-compromisable, the product lives to the expectation of the customer because quality and reliability paradigm are determined by the customer through the voice of the customer. When you look at it, the DFMEA plays a significant part. The process enumeration, especially with regard to the FEA application. Why I am saying that is because DOE and FEA combined together will give you a very strong, potent, lethal application. So you look at the DOE, you look at all the green segments, you will see the performance objectives, the design for performance, the design for life, and the tolerance optimization are areas where you would use DOE quite a bit. The constraints are going to be the cost of poor quality and cost of precision, the process capability, and the SOD from your DFMEA. Instead of the RPN, it is the severity, occurrence, and detection, right? Now, what is DOE? It's a design of experiment consists of planning the experiments, conducting the experiments, analyzing the output of the experiments, interpreting it, and the controlled experiments to evaluate the factors that control the value of the parameters or a set of parameters. So in other words, you have an input to a process, the process itself being defined, and the output or the outcome from the process. There are factors which influence the process and a result of which the output as well. The controllable factors are excess, while the uncontrollable factors like environment, corrosion, so many other things, they are uncontrollable factors. When we are doing an experiment, we are doing it under controlled scenarios. We are looking at the controllable factors when we are putting this together. So in other words, the parameters, the factors which influence the output in terms of the measurable parameters is what we look at in design of experiments. So planning this, now when we are doing an experiment, it is too prohibitively expensive if we were to conduct the experiments using physical prototype. This is exactly where the computer-aided simulation tools come of use, because there everything is controlled under the controlled parameters. So in other words, the controlled experiments today can be done digitally as compared to doing it manually, physically with many prototypes. Steps in DOE are: define the objective of the process. This needs to be very clear. Performance, return life, warranty, any which way you look at it. It could be a quality objective. It could be a reliability objective. Now you define the objective of the process. Set the target value for the process performance measurement. Unless we set the target value, DOE is of a fruitless exercise. And if possible, have it on continuous scale so that you can monitor it. Then you enumerate the design parameters that are affecting the process. As I told you earlier, specify the variation of each parameter in terms of levels. It could be high and low, high, median, low, any which combination you want. More the number of levels, more the number of experiments. Lesser the number of levels, more the interpolation between the levels. Are you with me? So depending on the model that you choose. excuse me. Then you develop the orthogonal arrays for the parameter design with number and the conditions for each experiment. Now conduct the experiments now that you have put the plan together with the identified variables and the factors, using the completed array to complete the array, collect the data to effect of performance measure. Then complete the data analysis to determine the effect of the different parameters on the performance measure. This is where many other models come into picture. Now, take the case of a pressure relief valve. The pressure relief valve has to activate itself when the threshold of a particular pressure has been achieved. Now remember, these valves are not designed for discrete states of pressures. The pressure in the line continuously varies. When the pressure in the line varies, then using discrete values to come up with this would be a no-brainer, would lead to failures subsequently down the line. So the performance objectives have to have range. The factors have to have range. The parameters influencing the performance, it could be tolerances, it could be the preload, it could be the length of travel, it could be temperature. For example, in this case, we design a pressure relief valve for room temperature. But what do? We start doing accelerated durability test and say 5 Hz pressure variation. I am going to test whether it works or not. Now continuously applying 5 Hz or 10 Hz increases the heat in the system. You have a steel body, steel spring, steel plunger, copper washers, brass restraining element inside. You have whole new can of worms because temperature now becomes important. The preload gets affected as a result of differential expansion. So what you think is the preload may not really apply. So the characteristic curves for the pressure relief valve, the response criteria, the pressure drop, the CV calculations, so many things are there that we need to look at. Now the problem becomes compound. If it is going to have different kinds of fluid medium, air, water, steam, oil, hot oil, any which way you look at, inert gas, compressible gas, incompressible units, fluids, any which way you look at, many factors come into play when it comes to the response of the system. Next, you look at the pulsating pressure. You have one more parameter which is coming into problem. What is that? Because it is not a discrete pressure, it is a pulsating pressure. The ratcheting takes place because of the spring-loaded valve. When the ratcheting takes place, noise comes into picture, the decibel levels. So now the frequencies come into picture. The mass of the moving unit comes into picture. The response time, again the mass comes into picture. In one time you may have to increase the mass, in another way you have to decrease the mass. So you have contravening dispositions in design challenges when it comes to this. This is exactly where DoE comes of use, folks. If we are looking at intellectual property development, if we want robust designs, DoE is the way to go. So if we have to do design without errors, DoE is the way to go. You can look at the tolerances which are coming up in each and every one of them. You can look at multitudinous DFQ and R objectives, like for example, the gap C, the misalignment A, leading to the misalignment in the spring. The misalignment in the spring leads to what? When the pulsation happens, the fluctuating stresses in the spring leading to premature breakage. When it breaks, the spring breaks into two pieces. Now you have two springs in parallel in series. The stiffness of that is not the same as the single element. The frequency goes all over the place. So these kinds of what if scenarios we need to look at upfront. The DFMEA covers that, drives that. verifies that, ensures that you avoid them, and the SOD is addressed in terms of parameters which we need to monitor. Then we look at each and every one of the drawings that we are putting together, the GD&T drawings that we do for every one of them, and making sure that the values of the tolerances that we give, the sequence of assembly that we use, have to be in alignment with Q and R. Once we put this together, then we start looking at the evaluation of the part level tolerances at the assembly level. So what you are looking at is the isometric view of the drawing that you would give to the customers, to the manufacturer to produce it. Now you will be looking at, if it is a supplier, you will be looking at the control parameters. They are control charts. If you are looking at independent parameters, then you will be looking at the scatter diagram to see the influencing coefficients. So many different ways to look at it. So you're looking at the plunger, the GD&T for that. There are different ways in which you can put it. The detail A provides for all the different ways in which you need to control the parameters, so that control the factors, so that the parameters that you are looking at from a measurable point of view are achievable, and they significantly stay on the median of the requirements. The Taguchi's method concentrates on the median. Though other methods are there, this is very popular because it is easy to adopt, clear. The cost of poor quality, the loss function is very clearly provided for, and it is easily deployable. Now let us look at this example of a flow regulator. You have the housing. As the number of components increases, as the complexity of design increases, more number of parameters need to be monitored, more number of factors come into play. DoE becomes the most sought after tool for development of those designs, specifications of those parameters, and the factors which need to be monitored. In this example, if you see this animation, watch carefully, you will see the piston moving from left to right, and as it moves, it goes and hits against the conical piece, stopping the flow. You see that? Now, the response time is important. The effectiveness of sealing is important. Right? So many aspects are there. So many failure modes are there. The pressure drop is there. Effectiveness of sealing, longevity, leakage. You want to minimize leakage or you want to eliminate leakage? We have to define those, right? These are performance parameters. Next is reaction time. The solenoid helps you to come up with the reaction time. Now, instead of looking at everything only from a mechanical point of view, we also need to look at the electromechanical part of it, where the electrical part of it, the electronics part of it also plays a significant part. In other words, DoE is applicable to electronics. It is applicable to electromechanical devices. The cross correlations between the factors on the mechanical side and the electrical side cannot be ignored. Again, DoE comes into picture. So you look at the partial drawings, you look at the significant contributors, you start delineating those drawings. The setup is determined by the datum reference frames as mimicked by the sequence in assembly, right? And then whether it is suppliers or it is in-house manufacturing, you will be in a position to look at the critical to quality parameters, and you will be able to gain information with regard to whether they are setting in the median of the specification limits, because the spread only helps you to understand how far the sigma levels or the tail extends. The prerogative is to sit in the median. Now in factorial design, you look at full factorial, which is expensive, and then the response surface analysis, which is typically what people will use. That way, you will be able to take the influence of the factors and conduct the experiments accordingly. One of them we are going to be doing is the response surface analysis now. Now, the tools that you can use to come up with while performing the DoE are the flowchart for delineating the parameters, the steps, and every step you will be monitoring the parameters, the input to the step, the output from the step, that you can monitor it. Then you can look at the fishbone diagram for your cause and effect analysis, because this is exactly where we look at how the IPR gets into the product, the experience from our organization, from the people in the organization, the control charts for the tracking parameters, the scatter diagram for the independence verification of the individual factors, because if there are interrelationship between the factors, this would come about. Then the appropriate models have to be chosen for your analysis of the output data from the variables that you have chosen. And then the Pareto for the significance, and then the histogram to see the process capability assessment to see if it is really performing within the specification limits and the control limits are in line. So using CAE to conduct the experiments is cheaper as compared to putting this together in terms of physical testing, because the uncontrollable factors come into play in physical testing while they are literally absent when it comes to CAE based experiments. In CAE based experiments, the variations can be brought in together. Nominally we do it only for the normal values, right? That is nominal values. But here you can bring the variations into picture. This is exactly where robust design comes into use. So employ your 3D CAD topology already in use. Identify the parameters that influence the output. Enumerate the constraints that would help establish the non-trivial values for the design parameters. Establish the relationship between design parameters and output parameters using the CAE tools. Conduct the DoE matrix and fill up the values using your simulation tools. It could be CFD, it could be FEA, it could be a combination, it could be multi-domain FEA, multi-physics problems. Perform the simulation to calculate the output parameters. Now, how good is your DoE value depends on how you have established your correlation between your FEA and CFD with respect to experimental values. This is where the procedure of the FEA comes into focus. This needs to be controlled. This needs to be delineated very clearly. Once this procedure has been put together, it is a question of repeatedly using these procedures for different factors, for varying those factors and getting your outputs and results. At EGS, we have been working with a lot of different customers in establishing correlations, whether it is frequency, life, predict the failure modes and face it on the field, or doing a root cause analysis after a failure has occurred, crossing 500 hours. Imagine how much money you have to spend to test something for 500 hours. At the end of the testing, what do you have? A failed specimen. You only have a conjecture with regard to what could have been the reason for the failure. Is it a one-of-a-kind failure or a predictive failure with regard to ductile yielding? We do not know. We can have only certain confidence levels. Now, in the R factor design, when we are looking at this, the life calculations, you will see the cycles to failure and the amplitude as given in the design textbooks. But when you look at the actual amplitude, one of the parameters, one of the factors that you will be using is the material parameters. So if the material parameter has a tensile strength varying between a certain two values, the yield strength varying between two values, the Poisson's ratio varying between two values. Poisson's ratio, people really don't pay attention. That tells you the crystalline structure inside, and also helps you to look at the ductile yielding before failure. It's a very important parameter. It is not used, it is just assumed. It's a huge thing. So when you look at every one of the areas, you will see that there is a variance, a distribution as shown on the right side. These can be factored in your DoE. So when you take together, so for example, you look at this pilot relief pressure versus the main relief pressure, looking at the values, response time, and you look at the duty cycle, you look at the cost of poor quality comes into picture. If you choose the cheaper one, 175,000 cycles, while the other one is 1,000,000 cycles. It depends on your service life expectancy in your parameters as your objectives. Now let us look at a simple example of a valve wherein we are looking at to look at the flow values and to look at the dimensional design factors are to be sized for the inlet pressure, the valve clearance to allow the fluid to flow through, and the size of the orifice diameter. These are the three parameters. Minimum force is required to open the valve. Maximum volumetric flow rate is required. So one is minimizing, one is maximizing, and the output response will be mapped using quadratic regression. Why? Because we are using response factor method, the factorial fractional factorials. So the factors are valve opening clearance. That value will be given in millimeters with a plus or minus value. Orifice diameter, flow through the valve, plus or minus. Inlet pressure, again a value with the variations, line pressure variation. The output is the force required to open the valve. Remember, we do finite element analysis in discrete states. But what we are looking at is continuous variation, not discrete alone. This is where DoE comes of use later on with contour plots. The volumetric flow rate is one of the output variables. So when we look at all these, we put the three parameters together, we put the two responses together, develop the finite element analysis procedure or the CFD procedure, and then we look at conducting the experiments. In this particular case, we will be looking at 16 to 17 parameters, and we do the analysis. We start looking at the results. We populate the table. Once we populate the table, we get the response forces and the volumetric flow rate for the different values as enumerated by the designer. Now for the DoE process, we use the box-Benken design, response surface modeling, one of the methods used. It allows the quadratic regression model without limiting the number of experiments. ANOVA method is used for the valve opening force calculations as shown on the right side. The optimal values of the inputs or the factors are arrived at based on regression. You see how beautiful this is? So in the design space, DoE helps you to arrive at the parameters, the nominal value of the parameters, the effect of the deviation from the nominal value towards the extremum, and their influence on the overall performance is clearly given here based on DoE. With simultaneous application of multiple factors coming into place, not one factor at a time, which is expensive. This is the power of DoE. So it helps you to come up with the optimality of the values. So later on, if a customer wants a change in design to come up with a new design, then you can always look at what are the performance characteristics there and change the parameters here, conduct this and automate this process so that you can get the results very beautifully. We went through a DoE process for fine blanking tooling design development. 256 different iterations. We automated the finite element analysis. It was a nonlinear finite element analysis because the fine blanking process is a nonlinear, material nonlinear, contact nonlinear analysis. So we automated the process and we went through the DoE and finally came up with the tool chart. Selection of tool based on the tool chart. This is how we did it with one of our customers. This is where DoE was used in that particular thing with regard to the wear life, so many different parameters. For example, you look at wear, failure by wear, because wear leads to leakage, wear leads to so many different problems downstream. Bearing, roller bearing, rollers wear, so many things. So you can look at what wear parameters, you measure it, you look at what is the measurement after so many, what should be the diameter after so many runs, after so many life cycles, And then you come back and say the influencing coefficients are the sliding velocity, the contact pressure, the coefficient of friction, temperature. Like that, you get the factors in picture. Now you start doing a finite element analysis and you start looking at the Hertzian contact stress and develop a VAR model based on the Hertzian contact stress. And then it's a two-part process. One is the CAE and the other one is the manual process. So any combination of these processes can be used to arrive at optimality of the specifications and ensuring that you are staying within the centrality of those specifications, because that's what drives the quality and the reliability of the product. So the benefits of this approach is that quality should be designed into a product, not inspected into it. Quality is not only for inspection, it has to be institutionalized inside the product at the design stage itself. This is what Taguchi said. And if we are looking at first time product, first time right, then we come up with this process institutionalized inside the organization. We are able to get the benefits out of it. Instead of using conjectures in the root cause analysis, you have definitive contributions from these parameters used on the 7 tools that I told you earlier. So it is not person specific, it is process centric. It's a clear understanding of the cause and effect. Strengthening of the product IPR, especially with Make in India, Atmanirbhar Bharat. It is possible only if we put these parameters together in proper perspective and develop products and technologies in this country using the know what and the know how approach. This is what will help the country in the long run, not paper to product manufacturing alone. Development of the drawing paper. Anybody can manufacture to a print, but developing the print requires a huge amount of discipline in terms of processes. And that is what DoE gives you a thrust upon. And consistency in quality and reliability can be done by design upfront if DoE is used as a mainstream in every one of the product development that we go through before we sign off on the drawings. It is important that before we sign off on the drawings, that all the parameters are vetted out. It is not a question of tolerance analysis. It is not a question of finite element analysis. Which one I should use? It's a question of combination. So the priority depends on the severity, occurrence, and detection, not anything else. The DFMEA dictates that, not the individual gut feeling. We tried to reduce the costs, but the problem is the cost of poor quality after the problem has been reported by the customer is so huge that it can either wipe out the product or the company. So in all these cases, if design people want to build confidence into their designs, if they want their customers to appreciate the robustness of their designs, then they have to institutionalize this as a part of their design and development process. So with that, we conclude the presentation now.